In this module, we are going to look at the problem of number representation. We're going to mainly look at converting from one base to another, but I want to look at this in a slightly more wider picture as to what numbers representation, etc. means. So the key thing that we are trying to do with number representations is we are mapping objects and concepts into representation. What we need is we need to have a one-to-one mapping so that whatever object we are talking about, I don't want two objects in here to be represented by the same thing, because in that case I won't know which object I'm talking about, and that's why I need to have one-to-one function in this setting. When it comes to numbers, I want you to understand that there is something that is factual and there is something that is representation. So here I have this object. Now there are different ways we can represent this object. We generally write this as this. I'm not pronouncing anything for a reason. We call it something like this. There are people who call it 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 this. Now, there is this object. There are people who call it this, this, and so on and so forth. So what we're doing here is we have an object. We're giving it a name, or in some cases, what we call numbers. Now, what name you give, it doesn't matter as long as you're giving the name consistently. And another thing that you're not allowed to do is you're not allowed to call these two objects the same thing, because then I don't know which object you're talking about. Let's take it a little bit further. Let's try to define addition. Okay, this is the addition fact, which is this object plus this object is equal to this object. Now there are different ways we write this. So we can represent it like this. We could represent it like this. We could represent it something like this. I'm not saying it because I will screw up pronunciation of more than half of the things. So I don't want to offend anybody by pronouncing words in languages I have absolutely no knowledge of. If we're adventurous, we could even write something like this. Now, for most of you, you will need to go look up the previous slide to see what this last thing is saying. But if you go look up the last slide, you will see that this sentence is valid. When it comes to object representation, some of the questions we will have to address are things like how many symbols are we going to need? What's the cost of representing? What is it that we're going to do with these representation? So for example, if I wanted to do addition, Roman numbers was probably a very bad idea, because trying to figure out that this addition somehow works is going to be a nightmare. So we would like to have representation that makes sense, especially to do at least arithmetic. And so we are going to focus on number representation. So in number representation, this is something you have been studying since kindergarten. This is something called place value notation or something. We usually write numbers with a base. In this case, the base happens to be 10. And because we have the base to be 10, we have 10 different digits starting from 0 to 9. And we write this number as 453 is 3 times 10 to the power 0, 5 times 10 to the power 1, and 4 times 10 to the power 2. We call this positional system because depending on where we write a number, its value changes, and that's why we have this whole place value system that you probably went through every grade in your elementary, high school, and maybe elementary, middle school, and probably even high school. Okay, so let's try to change the base. What if the base can be something other than 10? So do we have to have the base to be always 10? The answer is no. We have base 10 because we have 10 fingers. That's sort of how things seem to work better. What if I wanted the base to be 7? So that's basically what we're going to focus. So let's try to figure out. I had this object representation earlier. What is this number? Now, I know you're worried that I will make you count. No, I won't make you count. But if you do count carefully, and if I had done it correctly when I created the slide, the number of things in there are 125. So let's try to revisit how we can find this number without actually counting 1, 2, 3, 4, 5. Now what I'm going to do is sound a little bit counterintuitive, but it will come in handy to do what I need to do. So the way we're going to find how many objects there were is we're going to take this and create groups of 10. So if I create groups of 10, I told that there were 125 O's that were in my object. So if I created groups of 10, I will have 5 things that are left, and that 5 is going to form my least significant digit. So moral of the story so far is if I want to find the least significant digit, I'm going to divide the number by 10, and whatever is left, namely the remainder, that is going to be my least significant digit. Let's take further. How do I find the next significant digit? So we are going to represent this particular object, and if you count this, there are 10 O's in this. We're going to represent this by T, and I'm calling it T because it represents, of course, 10. And so in that case, the number that I'm going to have will look something like this. Here I have 12 of these T's and 5 of these O's. We are going to discard the O's and group the rest in groups of 10. So in that case, we will get these 12 T's is same as this one group of 10 plus 2 that is left. Beautiful. That means our next least significant digit is 2. Keep going further, the next least significant digit is 1, and I can actually keep doing this again and again and again. If I like the significant digit, I will get it 0, so I can write this number as 0, 0, 0, as many zeros as I want at the beginning because they anyway don't add any value, followed by 1 to 5, which is the actual number base 10. Moral of the story so far, I'm going to start with the number n represented by O's divided by 10. That will give me the least significant digit if I use the remainder. I take the quotient, reset n to be the quotient, and repeat until I find all the digits. Once again, we have reached the check before you go ahead slide. I want you to understand how we got each of the digits in the previous analysis.